inverse functions. Okay? Okay, finding inverse functions is one of the easiest things there is. There's only 2 steps. Step number 1, switch the variables. Step number 2, solve for y. So do step number 1 for me. Now do step number 2. Hold on. Yes, you do, Brandon. You got to solve that equation for y, which means you want to isolate y. What do you have to get rid of to isolate y? No. What's with y? Okay, how do we get rid of the 7? Divide both sides of the equation by 7. That's what you're doing. Okay? And that gives you y equals x over 7. Well, that's actually the inverse. In other words, because you switched the variables and solved for y, you got the inverse. So this is actually that. I don't know what kind of notation they're giving you, but that's always the way to solve for an inverse. You switch the variables and you solve for y. Okay? Give me another one. Like that. So more like this. Better? Okay. The difference is this is the, oh, excuse me. When I write it like this, the 1/3 is the base. When I write it like this, the base is 10. If the base is not written, it's 10. So there's quite a difference between those two. Okay. Now, this is one of the harder ones to solve, just because it is. So we'll still do the 2 steps. That's the first step. I'm going to rewrite it up here so I have, So do that. What do you get? The way you verbalize that is log base 1/3 of y, where y is called the argument. Okay. The argument is what? The log of what? So you have the log of base, you can have a base of anything, and then you have the argument. Okay. All right, now, solving this for y is not the easiest of tasks. You clearly have had logs, since the time that we have talked before. Correct? Okay. So, I'm going to go ahead and show you how to solve this for y, but it really requires us to have like a 20-minute conversation about logs. You and I need to talk about logs. You got to understand logs before you can get through your math class. Okay, and they're confusing. It's like a foreign language. But they're really not confusing. You just have to be directed correctly as to what logs mean. Okay. But the way I'm going to solve this, and it's not going to really make any sense to you, but if the log base 1/3 of y equals x, that means 1/3 to the x power equals y. In other words, it's the base raised to that exponent equals the argument. Let me give you an example. 3 equals the log base 2 of 8. That is a true statement. There is no variables in that. The log base 2 of 8 is a number. Okay? However, if I want to express that logarithmically into an exponential, then I take the base, raise it to that, so I get 2 to the 3rd equals 8. Is that a true statement? That means that is a true statement. And you will notice one thing about logs. Logs are exponents. Notice that the log base 2 of 8 is equal to 3. Well, 3 was the exponent. So the most important thing you need to be able to do with logs is to be able to translate between logs and exponential. Okay? Over here on the right, that's a log expression. That's an exponential expression. And you can always go back and forth between the two. They are saying the same thing. It's just that logs present unique opportunities to solve some of the math problems. And so instead of exponentials, they developed logs in order to go further in math. But in terms of your problem over here, we did the first 2 steps, did we not? We switched the variables and we solved for y. That means that is the inverse. Y equals 1/3 to the x power. Let's go back. I want to talk about logs. I don't want to pass this opportunity up because you really need to understand logs. Okay? All log discussions begin here. What is different about that expression, about any other expressions you've ever encountered? The x is in the exponent. This is not an algebraic expression. You cannot solve this algebraically. This is an exponential expression. Okay? It's like 8 equals 2 to the 3rd. That is true. But if I said to you 7 equals 2 to the x power, you would not be able to solve that algebraically because it's not an algebraic expression. We know the answer is somewhere between 2 and 3, right? Because 2 squared is 4, 2 cubed is 8. So x has to be between 2 and 3. It's got to be greater than 2 and it's got to be less than 3. And it's some decimal number. It's like 2.876543 or something like that. Okay? And the thing is that you have, without logs, you have no way of solving that. I'll give you a week, and if you don't employ logs, you're not solving this. And the reason is because you cannot solve it algebraically. The only way to solve it is with logs. Okay. Now, the way I'm going to solve that is I'm going to take the log, the natural log of both. Well, I'll make it easy and take the log base 2 of both sides. Okay. Now, remember that whenever you have an equation, you can do the same thing to one side of the equation as long as you do it to the other. So it's perfectly acceptable for me to take the log base 2 of both sides. Well, when I take the log base 2 of the right side, when you take the log base 2 of 2 to the x, you get x. So that's what x is equal to, if I wanted that. Now, if you have the right kind of calculator, you can go in and that's just a number. When you have logs of numbers only and there's no variables, that's a number that you can look up in a table or, in the modern age, a calculator. Don't confuse logs with variables. Logs are numbers. If I tell you the log base 10 of 7, that is a number. If I tell you the log base 2/3 of 8, that is a number. You can get that out of any calculator. Now, if I tell you the log base 7 of x, well, obviously that's not a number because we have a variable in there and we don't know what that number is. Okay? But if I were to say the log base 7 of x equals 13, well, now I can solve that by translating it to an exponential expression. That means 7 to the 13th power equals x. Well, you can get that number on your calculator, right? Do you know how to do that on your calculator? 7 to the 13th power? It's this thing here. It's this thing. What calculator do you have, Brandon? Okay, you can do it. TI-84 has this symbol on it. You have it in front of you? You should always have it when we have a session. Always have your calculator. A big number, right? Take 7 and raise it to the 13th power. What does it tell you? And what it tells you more. E to what? Okay, that means 10 to the 10th power. That's what that means. Okay, well 10 to the 10th power is a billion. So this is basically 9.68 billion. It's a big number. Okay, so that's how you solve exponential math on your calculator. And you'll notice that we were able to solve that logarithmic equation where I had log base 7 of x equals 13. I was able to solve it because that means that 7 to the 13th power equals x. And that's just a number we can get off of our calculator. But you can also get log numbers off your calculator. If I said, what is the log base 10 of 3? Do that on that calculator. Now, when it's base 10, that's your log key. When it's base e, that's your natural log key. So this is base 10. So go ahead and type in log of 3. No, it isn't. Do log of 3. Hold on, you were correct. I apologize, my mistake. I was the one that was getting it mixed up. Yeah, what was the answer again? Okay. And what that means is 10 to the 0.477 power equals 3. Well, does that statement make sense? Let's see, 10 to the 1 power equals 10. 10 to the 0 power equals 1. So yeah, that's between 0 and 1. So that does make a lot of sense. 10 to the 0.477 power does equal 3. Okay, so that's all logs are. Is there a way to express exponentials as log statements? And there's a reason somebody invented this. It makes math a whole lot easier. All right, give me another one. Any kind of problem you like. We got about 10 minutes. It's not to the x power, it's y equals log base 4 of x, is the way you pronounce that. Unless you meant this. Hold on. There's two different things. There's this one, and there's this one. Which one did you have? The first one. Okay. In other words, when you write the log without a base, it assumes that the base is 10. So the one on the right is actually log base 10 of 4 to the x power. The one on the left is log base 4 of x. Okay, and again, they want the inverse, correct? Oh, the domain and range. Okay. First of all, let's talk about domain. You can only take logs of positive numbers. What's the domain of this function? I'm going to say it again. You can only take logs of positive numbers. That means that has to be a positive number. And the domain relates to the x values. So what's the domain of x? I'm going to say it a third time. You can only take logs of positive numbers. You can take logs of all positive numbers. You just can't take logs of negative numbers, and you can't take logs of 0. So what does x have to be here? Has to be greater than 0. Okay? The range. When you take logs, let me graph it. That might help. That is the graph of y equal log base 4 of x. That's the y-axis. That's the x-axis. So tell me, first of all, which variable does the range apply to? Domain applies to the x. What's range apply to? Okay. Now, first of all, let's check the domain. We said x can only be greater than 0. Does that graph support that? Yeah. Look at the x values. Are there any x values at 0 or negative? No, there aren't. Our x values, and I'm talking about the x values that are on that curve. There are no x values on that curve that are 0 or negative. Okay? Now, let's look at the range. Make your eyes look up and down rather than left or right. When we were looking at the domain, we were looking at left and right. Now we're going to look at up and down. What are all of the values that y can be? All real numbers. Another way of saying that is negative infinity to positive infinity. Have you gotten into interval notation yet? This is interval notation. This would be more like saying y can be anything. There's various ways to express domain and range. Okay? At some point, you're going to get into interval notation because sometimes you have intervals. You don't have, one number to another number, or negative infinity to positive infinity. Sometimes you have certain intervals. And when you have certain intervals, the best way to express it is with interval notation. And that is the curve, the correct curve. So you gave them the domain. X has to be positive. You gave them the range. Y can be negative infinity to positive infinity. This thing keeps going up. Even though it looks like it flattens out, it always is rising. So if you go all the way to positive infinity on the x-axis, you'll go to positive infinity on the y-axis also. Okay. And this is very typical of all log functions. If I said, how do you graph this? Well, guess what? It looks just like what I just graphed. Okay? It can be a little different if I had the log of x minus 2, something like that. Well, now everything shifts to the right by 2 units, and so that graph would be a simple transformation, like that. Remember your transformations where you go horizontal or vertical, or you reflect over the x-axis, or you reflect over the y-axis. Well, log functions are going to be included in that. You're going to get transformations of log functions also. But more importantly, you're going to get certain rules about log functions that are very, very useful for all kinds of higher math. And that's the reason, the biggest reason we have logs. Although it's interesting. If I said to you, what is the log base 7 of 6? That is something that when I was in high school, we didn't have calculators that would tell us what that number was. You had to look it up in a book. At the end of every math book, they had tables. And they had log tables. So if you wanted to know what that number was, you had to look it up in a table. Now we have calculators, and you can put that into a calculator and look it up. Now, it turns out that in your TI-84, you can't do bases other than 10 or E. So you also need a change of base formula, which we can probably talk about next time. I don't want to run you over today. But we need to talk more about logs. So you need to make another session here to talk about logs, because there's a lot of, not a lot of things, but there's a few things about logs that I have not talked about here that are going to be critical to you. Okay? And the sooner we have a session about it, the more up to speed you're going to be on it and be able to follow it when they cover it in class. Okay, Brandon? Brandon, you have a good weekend. I will talk to you next time.